Who shall conceive the horrors of my secret toil as I dabbed among the unhallowed damps of the grave, or tortured the living animal to animate the lifeless clay? My limbs now tremble and my eyes swim with the remembrance. But then a resistless and almost frantic impulse urged me forward. I seemed to have lost all soul or sensation, but for this one pursuit. I collected bones from charnel houses, and disturbed with profane fingers the tremendous secrets of the human frame. The dissecting room in the slaughterhouse furnished many of my materials, and often did my human nature turn with loathing from my occupation, whilst, still urged on by an eagerness which perpetually increased, I brought my work near to a conclusion. It was on a dreary night of November that I beheld the accomplishment of my toils. With an anxiety that almost amounted to agony, I collected the instruments of life around me, that I might infuse a spark of being into the lifeless thing that lay at my feet. It was already 1 in the morning. The rain pattered dismally against the panes. My candle was nearly burnt out when, by the glimmer of the half-extinguished light, I saw the dull yellow eye of the creature open. It breathed hard, and a convulsive motion agitated its limbs. Frankenstein, the modern Prometheus, was written by Mary Wollstonecraft Shelley. She's the one on the right there. And this is Boris Karloff, I think, in one of the Frankenstein movies. Frankenstein, of course, was the scientist. This is Frankenstein's creation, who was pulled together by a lot of inanimate body parts and given life by applying electricity. Where'd she get this idea? Well, back in the day, scientists would almost do it as parlor tricks. They'd come around and entertain people by doing things like applying applying electrical differences, potential differences, running current through the muscles of dead frogs, and it would make those legs jerk. Now, this wouldn't work too well, I guess, because I don't really see what's causing the voltage. But there would be current running through a frog's leg, it would move, and they'd say, see, it's coming back to life. Through electricity, we have the ability to bring things back to life. So that was what inspired her. We're going to be talking about static electricity. And static electricity is something that, well, when I demonstrated on my arm when I was reading Frankenstein, I was using a TENS unit, which basically just puts a little jolt of current, makes electricity flow through my arm. Defibrillation units work on very similar principles. Static electricity is not about the constant flow of current. It's really just talking about taking electrical charge and moving it from one point to another, or having it reside in one place. So that's what we're going to talk about first. Eventually, the principles that we learn from static electricity will help us develop the concept of electric circuits and all the electrical tools that we have. Electric charge is the basic concept behind electricity. It has a symbol, little q, and the unit is coulombs, capital C, coulombs, so named after a French guy. Charges can be positive or negative. You probably knew all this stuff. So we measure the charge of something by saying how many coulombs it has and if it's positive or negatively charged. The building blocks of electric charge are the protons and electrons for the purposes of this class. There are smaller subatomic particles that go into electrons and protons, but really for the purposes of this class, electron is the smallest negative charge, proton is the smallest positive charge. What's really nice coincidence is they both have the same magnitude. The electron is negatively charged, and we call this thing the elementary charge, 1.6 times 10 to the negative 10 to the negative 19 coulombs. And that's the building block, because everything you see around you has a charge that is a multiple, positive or negative, but an integer multiple of that number. Why? Because we can only produce materials that have integer electrons and integer protons, positive integer, countable numbers of electrons and protons. So you can see if I have 2 electrons, it's going to be twice this. If I have 3 electrons, it's going to be 3 times this charge. Electron has negative elementary charge, proton has positive elementary charge, and that is the value of the elementary charge. You can see it's a really, really, really small number of coulombs. A coulomb is a big thing. So most of the charges that we're going to end up dealing with are going to be in the microcoulombs and nanocoulombs and even picocoulombs, because you need a whole bunch of electrons without any protons matching them to get a large charge, to get a large negative charge. So what do we mean by charge of object? Well, everything's made up of electrons and protons. So in this case, we've got most atoms have equal number of electrons and protons. Well, if you had minus 1.6 times 10 to the negative 19 and you add it with positive 1.6 times 10 to the negative 19, the total charge of those two is 0. We say the net charge is 0. Well, they're almost all matched up. So almost everything you see in the room is very, very close to neutral, very close to no net charge, because it has the exact same number of approximately same number of protons and electrons. So let's say if we had a billion protons and a billion electrons in this room, well, a billion times positive 1.6 times 10 to the negative 19 plus a billion times negative 1.6 times 10 to the negative 19 would mean we have no net charge, 0 total charge. If you have one more proton than electron than proton, if for some reason we brought in an extra proton, or I keep saying that wrong, if we bring in an extra electron, now I've got 7 electrons, 6 protons. I could add up the total charge of these and the total charge of these, but it would end up being the same as the charge of this unmatched electron. In other words, 6 protons and 6 electrons have partners. This one doesn't. So the net charge would be 1 negative elementary charge. Okay, similarly, if we take that away and we add another proton, then it would be a net charge of 1 positive elementary charge. So this atom, in which there are usually equal numbers of protons and electrons, and it's very, very hard to add or subtract a proton, so that's a really bad example. Really what I would want to talk about is, let me get rid of that. We start with this atom. The way I would give an atom a positive charge would be by removing an electron, taking it somewhere else. Then this atom would have a net positive charge. So that's an important thing to know. Protons kind of form the bulk of materials. Electrons are the things that can most easily move from one atom to another. So electrons are the things that do the moving. They do the work, basically, of electric machines. It's electrons moving from place to place. There are exceptions. For example, a positive ion here could be moving. This entire atom could be flowing, like ions flowing through water would mean a positive charge is moving. How are they interacting? Well, this is probably easy to know. The positive charges repel each other. Negative charges repel each other. So we say that similar or like charges repel and opposite charges attract each other. Okay, well, wait a minute. Let's go back. Look at this. Why aren't these repelling? Well, that's because there are different forces that hold a nucleus together. And by the way, I'm left out neutrons in this whole business. So these protons reside in the nucleus of the atom. The electrons actually are zooming in and out, I believe, of existence. But they're definitely moving around but they will generally remain part of this atom, and that's what defines the atom, is the protons and the electrons. Okay. Then let's talk about how charges move, and let's talk about conductors and insulators. Well, if you look at the insulator, that's kind of what we think of. Think of many more electrons and many more protons involved in this. But here they just model it as one electron going around one proton, or a bunch of negative charges going around a bunch of positive charges. In an insulator, those electrons are really hard to pull off. So if I bring a positive charge over there, those electrons, they might spend a little more time on this side of the atom, but they can't really leave the atom. Whereas in a conductor, there are some negative charges that can freely move over towards the positive. They're attracted by the positive charges. Notice that the positive charges in both of these don't move. They make up, again, the bulk of the material, the structure of the material. The electrons, and not all electrons, we call them valence electrons, and sometimes we call them free electrons, are much more able to move from atom to atom within the metal. So conductor, the free electrons, which are just a small portion of all of the electrons, they can move, but in the in the insulator, they are more tightly linked to the atom, so they can't move as well. If I pull that away, those electrons will more randomly space. The free electrons will more randomly space in the metal. And we'll talk a whole lot more about motion, charge motion within materials in a future lesson.